Hello, my name is Andrew Young, and today I will be discussing the BCS theory of superconductivity. BCS is just an abbreviation for the last three names, or the three last names, rather, of the physicists who discovered the theory. That is John Bardeen, Leon Cooper, and Robert Schrieffer. This was proposed in the late 1950s, and later in the 1970s, they won a Nobel Prize for this. And a little fun fact, John Bardeen is one of the only four people ever to win a Nobel Prize twice. He also ends up winning a Nobel Prize for the invention of the transistor, which is one of the most important discoveries ever, actually. So here's a little timeline of my presentation just to see what we're going to be learning and in what order. So first, I want to talk about just some background information in order to understand what will be going on in BCS theory. Next, we will be talking about what BCS theory actually explains and how it actually works at the particle level. Thirdly, we'll be talking about why BCS theory and superconductivity are important and how it applies to the modern world. And then lastly, I will be opening the discussion for questions. So first off, I want to talk about what is an electrical conductor. Now, if anybody in the audience wants to just give in their own terms a simple definition of an electrical conductor, feel free to raise your hand and share. Yes, so electrical conductor is basically just a material that conducts electricity. That's just a simple definition of it. Now, a good example of electrical conductor would be a metal, right? Metals, we all know growing up, are very good electrical conductors since electricity could travel through it very fast. Now, I want to talk about what is electrical resistance. If anybody else wants to share in their own terms of what electrical resistance is, feel free to raise your hand and share. Yes, so electrical resistance is basically just the measurement of how hard it is to pass electricity through a material. Now, let's have just a simple example. Let's say we have a metal and it has some type of resistance. Now we're going to shoot 10 amps of electricity through this metal to come out the other end. Now, when we shoot this 10 amps of electricity, only 6 amps come out the other end. Why is that? Well, that's because of the resistance in the material. There is a net loss of 4 amperes in the metal. So as we could see, resistance causes some loss in efficiency. Now, electrical resistance has always been proportional or directly proportional to temperature. Why is that? Well, at the particle level, electrical resistance is basically just the collision of electrons. Those collisions of electrons, we call that electron scattering, are explained through this image. So take this image. We have these big blue circles. We're going to say those are the atoms of the metal. And then we have these small silver circles. We're going to say those are electrons. Those are the atoms of electricity. So these electrons have a trajectory or a path that they follow in order to get out the other end. Now, sometimes when they're traveling, they bump in or they collide into these atoms of the metal, or they can collide into their own, or they can collide into other electrons. Now, these collisions, what we call electron scattering, is resistance, since when they collide, they lose their path, and when they lose their path, they never come out the other end. And that's what accounts for the net loss of electricity. Now, this doesn't explain why temperature is related to resistance. So let's talk about temperature. Temperature is essentially just the vibration of atoms. So let's say our metal has a very high temperature. That means these blue atoms, these blue atoms are going to be vibrating or moving way more than usual. So if they're vibrating way more than usual, that means there's a higher chance that these electrons will collide into these atoms. And when they collide, that means that they're going to have some net loss in electricity, which means there's going to be high resistance. So we take a look at this graph of a conductor. It's directly related, temperature is directly related to resistance. As we can see, as resistance increases, temperature increases. And that's because, as I just said, when the temperature is high, there's a higher vibration of those atoms in the metal, which means there's a higher chance of collision. which indicate when collision is, like I said, is just resistance. Also, as resistance decreases, temperature decreases. As temperature decreases, like I said, atoms will vibrate less, which means there's a less chance of collision, which means less chance of electron scattering, which means less chance of resistance. So now let's talk about Heike Onnes, who was a Dutch physicist in 1912 that discovered that in some materials, after or below a certain temperature, resistance drops completely to zero. Now, Heike Onnes just discovered superconductivity. This temperature that we drop below is called the critical temperature, or T subscript C. Now, Heike Onnes discovered superconductivity and ends up winning Nobel Prize for this, but he never explains why this happens. He just found it out that it exists. And that's where BCS theory comes in. BCS theory explains what is actually happening at the particle level. Now, one last concept to just keep in mind before we start learning BCS theory is just a simple electromagnetism concept of how opposite charges attract and how like charges repel. And we know that each particle has, a certain charge, either positive or negative. And when they repel, they have some repulsion force. So two positive atoms obviously will repel, and then two opposite charges will attract, and they have some attractive force. Now let's begin to talk about BCS theory. Now let's take this image on the left first. So these blue atoms are, like earlier, will represent the atoms of the metal itself. And then the red atoms will represent the electrons or the particles of electricity. So as we all know, electrons are negatively charged, and then these atoms of the metal will be positively charged. And as you can see, when the electrons are traveling through the material, they will attract these positively charged atoms of the metal and bring them closer to each other, and that is closer to the electron. Now let's look at this image to the right. The very small circle will be the electrons again, and the bigger circles will be the atoms of the material. So when these electrons travel, they're bringing these positively charged atoms closer. And when all four of these positively charged atoms are closer, they act as a big positive charge. And they have some type of big positive cloud indicated by this red type of cloud here. And when they have a big positively charged cloud, that attracts an electron further, and it comes and it pairs with this electron. Now, this is the most important part of BCS theory, that this huge cloud will attract other electrons to come and pair with the electron in the middle. Now, these two electrons are bonded together. And since they're bonded together, they have a very strong bond, this strong attractive bond, as we said earlier, the attractive force. They have a very strong attractive force between them, and they become paired, and we call these pairs Cooper pairs. Cooper being Leon Cooper, who discovers this. And now that these are strongly bonded together, these can travel through the metal without being slowed down. Now, if they bounce into other atoms or if they bounce into other electrons, this bond is so strong that it doesn't affect them. And now these electrons can travel through the material unhindered. And that's why there's no resistance at all. Now imagine if, millions of electrons are paired together and they're not, and they're very strong and they won't be bothered by collisions. Now all this electricity gets to flow through without any resistance, and that's very efficient and that is very important for modern day technology. So that is the very basic. Oh shit. I will make a part 2 of this video. I am running out of time.